Hello everybody, this is the second video clip for chapter 2 of the cost calculus for business 2. Okay, previously what we have learned is like how to draw a region representing the linear inequality. Okay, for example, if you talk about this linear inequality, if your x is 0, your y is 3, so this is the y-intercept. If your y is 0, your x is -3, so here's the x-intercept. Okay, so you have this straight line, and this straight line is actually the straight line for y minus x equals to 3. Okay, this one is y minus x equals to 3. But if you need this inequality, then you are going to plug in one of the point in either this lower region or the upper region. But you may see that the one with a lower region will be easier because this one is 0, 0. So as your x is 0, your y is 0, you have 0 less than or equal 3, which is hold, okay, the inequality hold. So it means that the region under consideration, it must be the region including the point that you just do the test, okay. So it means that here is the region that you're talking about, okay, this one. All right, so what we are going to do for this clip is that we are go back to this example again, the first example that we have considered in the previous video clip, okay, on the first one. All right, which we are going to maximize our profit under these three constraints, okay, which we have this constraint like this, okay. So this is for your machine A, for your machine B, and for your machine C, and of course your X and your Y, they are the number of units that you produce, so it must be non-negative, okay. And the profit is 4x plus 6y, okay, and you need to maximize your profit. So let us try to draw a region under consideration so that we know like which point x and y that we are going to test for our maximum profit, okay. So your first one, let me just draw a big x and y plane. However, please forgive me because even though I try to draw a big one, but later on it will be a small region again. I don't know why. Okay. So first of all, I mean these two condition, as we told you previously, that it determine that the point under consideration is all the xy points, okay, that is in the first quadrant, okay. So it means that it is in this quadrant, okay. So you don't need to consider the one outside, okay, only in this quadrant, the first one that we are going to look for. And this one here, if your x is 0, your y immediately is 180. So let's say that right here 180. And if your y is 0, your x will be what? If your y is 0, so you got 2x equals to 180. So your x, it is 180 over 2, which is 90. So 180 is 90, let's say it's right here. And here's the one. Okay, actually, I mean, this is the line, 2x and y equals to 180. Okay, and you need to determine whether you are going to use the upper one or the lower one. So again, if you look at the lower one, you see this 0, 0 point, right? So you plug in x to be 0, y to be 0. So you have 0 less than or equals to 180, which is hold, okay, which is true. So it means that the region under consideration must include this 0, 0, okay. So it means that you are going to use the lower part, okay, the lower part. So let me just write down here to indicate that you use the lower part of this straight line. The other line is this one. So if your x is 0, Okay, you got 2y equals to 160, so your y, it is 160 over 2, which is 80. So 180 is right there. 80 maybe right here. Okay, and if your y is 0, immediately your x is 160. So this is 90, right? So 160 maybe somewhere here. Okay, over here. Okay, and forgive me if I have to, you know, draw it one more time. Okay, so this one is what? X and 2y equals to 160. Again, you just plug in, I mean, because there are two regions, and the region below including this point 0, 0. So you plug in 0, 0 here, it will be less than or equals to 160, which is whole. So it means that the region that you will choose, it will be the one that including this 0. So of course it will be this one. So all together it must be this region already, you see, because this one also, you know, need the one below, right? I'm sorry, this blue one, you need the one below the blue, and this one you need the one below the black. Okay, so the intersection, all right, and it is inside your first quadrant, so it must be this region. Okay, the quadrilateral like this. Another one is your x and y equals to 0. Okay, so equals to 100, sorry. So it will be if your x is 0, your y is 100. Okay, your y is 100 somewhere here, and if your y is 0, your x is also 100. So it will be something like this. Okay, let me just, okay, so it will be what we don't know is that whether it is really this line, the one that I draw, or the line that will passing through that point, or the line that is passing, you know, above that point. You need to really determine. So to determine that, you are going to find all the intersection point of these three lines. Okay, so the black the red one, let me just indicate first that your red one, it is what, x and y equals to 100. Okay, your red one here is x and y equals to 100. So let's look at your blue, which is 2x and y equals to 180, and your black, okay, which is x and 2y equals to 160. So if you want, you can use the matrix like what we have learned before, but of course we don't really need to, right? So this one you will multiply it by 2, so you have 2x and 4y equals to 220, and then you do a subtraction, so you have a 3y, right, to get rid of your x, and 320 and 180, so it is 140. Okay, so this one, your y is 140 over 3. Okay, and which is about 46.7. Okay, here's your y, and your x, it is a what, you can just plug in here. Your x is simply 160 minus 2y. It is 160 minus 280 over 3, so which becomes what, 160 and 3 minus 280, so it is a 200 over 3, which is about 66.7. Okay, so here it is 200 over 3 and 140 over 3. All right, so how about the blue and the red? Okay, So let's look at the intersection between the blue and the red. Okay, so the blue, it is 2x and y equals to 180. The red is x plus y equals to 100. So you can just simply minus. So you have your x equals to 80. Okay, and immediately your y is 20. Okay, so don't forget that this one, your x is about 66.7, your y is about 46.7. so here your x is 80, so it is of course on the right of 66, right? And your y is 20, so of course it underneath your 46. So this, I mean, this point is correct. So this one, your x is 80, your y is 20. Okay, next, to do the black, which is x and 2y, and the red, which is x and y equals to 100. This one, it is a 160. Okay, so again you can simply do a subtraction, right? So you have your y equals to 60, and then your x immediately is 40. Okay, so right here, this point, okay, your x is 40, so it is on the left of this 66, so it is correct. So here's 40, and your y is 60, so it is above that 46. Okay, this one, so the intersection is correct. So now don't forget that we still need to determine the region for your red, right? Your x plus y less than or equals to 100, is it? Okay, so either you are going to choose the one below or the one above. Okay, so again you just choose your easy point 0, 0, plug in here. So you have 0 and 0 less than or equals to 100. It is whole, so it means that you are going to use the region include this 0, 0 point, so it is the one below. Okay, that is the one below. So here, if you really take a look, okay, so the blue also need the one below, the black the one below, and the red is also the one below. So it means that altogether it must be this region. Okay, it must be this region, okay, containing this point, this point, this point, this point, and also this point. Okay, containing 5 points. You see, 1, 2, 3, 4, 5 points together like this. Okay, so this one sometimes is called a bounded region. A bounded region. Okay, it is a bounded region. All right. Okay, and if you want, okay, then you can take a look at this one. Okay, I mean it is pretty much the same, but the picture is just look nicer. Okay, because we use the program to draw it. Okay, and this region, the region that satisfy these 5 inequality, it is called a feasible region. A feasible region. So it is all the xy in this region that we are going to plug in into this equation. Okay, so that it will make a maximum profit. Okay, however, how are we going to do? Because actually the points, I mean, you have a lot of points, okay, to consider at the first place. Okay, so let me just look at this one carefully. Okay, let me just rewrite it in terms of y equals. Okay, so this one you move it over there, so you have negative 4x and what, negative 4x and p, is it, over 6, p also over 6. Okay, so if your x is 0, okay, if your x is 0, your y is p over 6. Okay, so it means this is your y-intercept, right? This is your y-intercept. If your y is 0, okay, if your y is 0, your x intercept, okay, if your y is 0, your x intercept will be p over 4. And because your p is a profit, then it means that your p must be positive, right? So your p over 4 will be a positive number. So it means that one of the line, okay, representing this profit function can be this kind of line, okay, can be this kind of line, okay, and the slope, it is actually negative 2 over 3, which is not the same as the slope here or there or there, okay. So this line is the red line that is not parallel to all these constraints, okay. So I mean, if we're looking at this line, okay, so it means that all the xy point on this line, okay, all the xy point on this line will give you this profit of p over 6, you see, okay, p over 6. So if you move your line, okay, this line, if you move it up, okay, parallel, I mean do the parallel translation just like this. So it means that the cutting point, the y-intercept is higher, so your p over 6 will be more, is it? You know what I say? So it means that comparing with the previous line, okay, the line that you just draw, this one, a new one, will give you a more profit, okay, along these x and y points here. However, can we use all these points to be your solution? You cannot, because right now what you consider point that you can use is only the one in this feasible region, okay. So what does this mean? Instead of going higher to have more profit, you need to move it below, okay, because even though this one gives you higher profit than this one, but you are going to use this one because it at least having something in the feasible region, is it? Okay, so what you are going to do is to move this one down so that it will touch the feasible region, okay, and if as it touch, then it may contact this point, 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 and it may contact this point as well. And of course it will, you know, along this region several lines, right? However, as you move down, what happened? As you move down, your p over 6 will be less and less and less, you see, because your p over 6 is the intersection of the y-intercept, right? So you need to find the first one that contact with your feasible region, okay, the first one that contact your feasible region, and it is the highest y-intercept that you can think of, so that it will give you the maximum profit, you know what I say, okay. And you don't really need to look at all this, okay. So I mean, as we are drawing not that good scale, then I mean this line that you may see that, hey, it should contact this one first, or we're not so sure it should contact this one first or not, then all the point that we are going to consider will be only the corner point of your feasible region, okay, or the corner points of your feasible region. Of course this one included, okay, even though it is 0, okay. So all the 5 corner points will be the one that we are going to evaluate for your p, okay, and see which one is the maximum, okay, see which one is the maximum. So that will be the one that it contact first, okay. So do you remember all the points, okay, all the points? Here we have your E as 0 and 80, okay. Here your A is the intersection between two lines, remember, which is 40 and 60. Your B, it is 80 and 20. Your C, it is 90 and 0, and your D, of course, it is 0 0. Okay, so what you are going to do is to plug in each and every point, okay, into your P. Okay, for example, 4 and 40 we got 160, and 6 and 60 you have 360, so you got a total of 520. Okay, 520 for the profit at this particular point A. For a B, if you plug in 80, so you have 32, 320, and you have another 120, so you have 440. Okay, this is a profit if you're talking about the point B. If you're talking about the point C, so you have 4 and 90, which is 360, and this one is 0, so you have a profit of 360 if you do this one here. Of course, if you do this one there, you y is 80, so you have 6 and 80, which is 480 is a profit for this point. And for the origin 0 0, you have no profit 0 here. So which one is the maximum? Right here is your maximum profit, is it? Okay, at this point. So it means that you are going to produce, you remember what is your X, here's your X, here's your Y. You are going to produce a manual widget for 40 units, okay, and electronic one for 60 units, okay, so that it will still under the constraint of your machine ABC, and also it will give you a maximum profit, just like that. Okay, well, right. So to find the optimum solution, okay, we usually given a linear programming problems, okay, and you are going to draw a region. Usually what we are going to encounter is a non-empty feasible region. If it is bounded, then the optimum solution always exists, okay, always exists at a corner point. By optimum, it can be either max or min, okay, it can be either max or min, depends on your problem. However, there'll be some other region, as we did before, that it is unbounded feasible region. The optimum solution may not exist, okay. However, if it exists, it still occur at the corner, okay, still, even though it is unbounded, maybe like this, okay, maybe unbounded like this, still the optimal is somewhere at the corner, okay, not somewhere that is beyond your boundary, okay. Another case that may possible to occur is that you may have an empty feasible region. Then of course, if there's no x and y that satisfy your constraint, then you cannot have any optimum solution, okay. So this is the example of the empty feasible region. For example, this one, x and 3y equals to 20. So if your x is 0, so you have 3y equals to 21, sorry, and your y is 7. So here is your y is 7, okay. If your y is 0, your x is negative 21, so it will be somewhere here. So of course the straight line that we're talking about, I mean negative 21 somewhere here, so this is the straight line, okay. However, I mean your x and your y, it is in the first quadrant, so we just cut your line right here, okay, and the one that we consider is the one above or the one below. So for the one below, you see that you have 0 0 as an easy point to test. So as you plug in your y to be 0, your x to be 0, you have 0 greater than or equals to 21, which is not true. So it means that the region that you want to include is not the one that passing through 0 0, so it must be the one above there, okay. So it means that you just use the one above, just write that. How about this one, x and y equals to 5? If x is 0, your y is 5 immediately. If your y is 0, your x is 5 as well. So you have this line. Again, for this line, you got the one above and the one below. And for the one below, you have 0, 0 as an easy point to plug in. Okay, so you have 0 less than or equals to 5, which is hold. So it means that the region that you need is the one including this point. So we have this one. Okay. So I mean, for this region, it is the one above. For this region, it is the one below, and it has no common points x and y. Okay, so it means that this one you have an empty feasible region. So if you want to either maximize or minimize this objective, then we has no solution for this optimization problem. Okay. Another one is the unbounded feasible region. Okay, the unbounded feasible region. Oh, I'm sorry. This is still bounded feasible region. Okay, the bounded feasible region. I mean, it is like the one that we did previously. For example, if you have this constraint, again, your x and your y are non-negative, so you just consider the first quadrant. Okay, so if your x is 0, your y is 8, so right here. If your y is 0, your x is 4, so it's right there. Okay, and then you just draw the line here, and again you have the one above and the one below, and the one below it is including this point 0, 0. So you just plug in, you got 0 less than or equals to 8, so it means that a whole, so you need to include that point, so you need the one below. Okay, this line, right? How about the second one? If your x is 0, your y is 12 over 3, which is 4, so it's right here. If your y is 0, your x is 12 over 2, which is 6, 6 is right there. So you have this line. Okay, again, for this line you have the one below and the one above, but the one below contains 0, 0. So you test your 0, 0 point by plug in, so you got 12, I mean 0 less than or equals to 12, which is true. So the region that you need to include is the one passing through this 0, 0 point. So it means that you will pick up the below region. And of course, I mean, from this one, I mean this region over here and this region over there, the one that intersection, it will be this quadrilateral here. Okay, so you got 4 corner points, okay, which is your 0, 4 for D, and this one, and 0, 0 of course, and the 4, 0 for the B. How can we find this one? So you are going to solve the system of equation 2x and y equals to 8 and 2x and 3y equals to 12. So all what you do is just do a subtraction, right? So you have 2y equals to 4, so your y is 2. So as your y is 2, you just plug in here. Okay, so you have 2x is 6 and your x is 3, so you have a 3, 2 for your intersection point here. And then you are going to just plug in into your objective function to see which corner points, okay, will give you the maximum. Okay, will give you the maximum. So for example, if you plug in A, of course, I mean it is 0, 0, so everything will be 0. If you plug in B, okay, which is 4, 0, so you got 12, right? Have 12. If you plug in C, which is 3 and 2, so you have 9 and 2, which is 11. And your D, which is 0 and 4, so you have a 4. Okay, so this one, the maximum, is the one with your point, with your corner point B right here. Okay, just keep in mind that sometimes the point that gives you the maximum maybe is the point that, you know, it is the either a y-intercept or the x-intercept, so it can be any corner. Okay, so it doesn't mean that it must be the weird corner that you need to, you know, the difficult corner that you need to solve for it. You know what I'm saying? Okay, so it can occur at this one, which is the easy corner that you can find out. All right. Okay. And the next example is for the unbounded region. Okay, for the unbounded region. For the unbounded region, if you need to minimize this objective function under this constraint, so let's see what kind of constraint that you have, and also your x and your y are in the first quadrant. So if your x is 0, your y is 4 over 2, which is 2, so it's right here. If your y is 0, your x is 4, so you have it here. Again, for this line, you got the one above, below and the one above, and you can pick up 0, 0 as your easy point. So as you plug in, you have 0 greater than or equals to 4, which is a contradiction. So it means that the region under consideration is the one that not included 0, so it must be the one above. So here you need the one above. How about the second one? If you this one is a little bit confusing. I mean, if you find the intersection, if your x is 0, your y is 0. If your y is 0, your x is also 0, so you have only one point. So you need another point. Okay, for example, if your y is 1, okay, your x will be 2, you see. If your y is 1, your x immediately 2. So you have 1 and 2, 1 and 2 here. Okay, so after that you can draw this point. Or if you x is 2, okay, if you if your y is 1, your x is 2, so you have 2, 1 here. Okay, and then you can draw this line. Okay, and again this line, you have the one below and the one above. However, each below and above is not include the 0, because the 0, the origin is on the line, so you need to pick up one of the point. For example, this 2, 0 here. Okay, so you plug in 2 minus 0, okay, because your y is 0, it is greater than or equals to 0, so it means that the region that you need including this point here that you make a test. So it means that you need to pick up the below 1. Okay, so you pick up the below 1. So it means that the region under consideration is this one. Okay, which is unbounded. Okay, which is unbounded. So we are going to find the minimum, either the minimum and the maximum of this objective. So how are we going to do it? We will do the same thing. We just rewrite it in terms of y. So you have y equals to negative 10x over 2 plus your z, okay, the one that you need to maximize, over 2 again, or you have negative 5x plus z over 2. Okay, so it will be the line that is, you know, if your x is 0, you are going to get your y-intercept as z over 2 somewhere here. Okay, and if your y is 0, your x will be z over 10, and because your x and y are all positive, then your z must be should be positive. So it will be something like this. These are the line. Okay, and this one actually the one that we wrote it for you. Okay, so what does this mean? It means that as you, so let me just draw it here. This is negative 5x and z over 2. Okay, so as you continue your y-axis, okay, and you continue your line here, this one will be your z over 2. Okay, and if you move it along, the feasible region, okay, so you move it up here. For example, let me look at this one, then your z is more, right, and because your feasible region is unbounded, so you can keep moving your objective line away, is it? So you can do more and more and more. So it will cut higher and higher z. So as you cut the higher and higher z, so it means that you have more value of your z, right? A more value of your z. So you have more and more maximum, is it? However, can you reach the highest value? You cannot, because your region is unbounded. So you can keep doing, okay, I mean for forever, okay, and you cannot reach the highest z-intercept, okay. However, if you're moving down, as you move down, you got a lower z, right, and you can move up to this point. You cannot move beyond, because this one is not in the feasible region, okay. So here at this corner point, you hit the last feasible region. So this one, it means that you have the lowest y-intercept, which is the lowest value of z, okay. So it means that for this problem, your z has no maximum, but it still can find the minimum because of the behavior of the objective line right here, and the minimum will be along the corner, okay, which is now you got only two corners. The first one is 2 1, the second one is 4 0. So you just plug in the 2 1 into here to your z, okay. So you have 20 and 2, so you have 22, and if you plug in 4 there, you get 40. So the maximum, the minimum one will be this 22, okay, at this point, right? And sometimes, okay, you may have multiple optimum solution. Why is that? Because I mean, as you move, you see here, you do the moving of your objective line, right? If the objective line happen to be the same slope as this line, okay, for the feasible, as a boundary of the feasible region, then it means that it's not only passing through the corner, but it passing through the whole boundary here, okay. So it means that each and every point, not only at the corner, but each and every point on this segment, it is your solution, right? So that will be like some rare case that your objective function parallel to your some of your constraint. For example, this constraint, okay, if your x is 0, your y is 2, can you see? So you have it here. If your y is 0, your x is -8, so you got somewhere here. So that's why you have this straight line. But your x and your y are in the first quadrant, okay. So you need to determine the above or below that line. And of course, this 0 again. So you plug in, you got 0 less than or equals to -8, which is not true, right? Okay. So the region under consideration cannot include 0. So you use the one above. How about the second one? As your x is 0, your y is 8, right here. As your y is 0, your x is 16. So you have this line. And then again, you need to determine whether above or below region that you're looking for. So your below region including 0. So as you plug in, you have 0 less than or equals to 16, which is okay. So it means that the region must include this one. So you are going to use the lower region. And of course, I mean, the thing that intersect between these two will be this triangle, okay. But if you look at your objective, okay, it is y equals to -2/4x plus your z/4, or -1/2 x plus z/4, okay. And this one, you are I mean, if you look at only the line, your y is equals to x/4 and 8/4, right? And this one, your y equals to negative x over 2 and 16 over 2. So here, can you see that this one and this objective line has the same slope, okay? So the objective line has a negative slope, so it means that the objective line, okay, it will be the line that is going down like this because of the negative slope, and it must be parallel with your x plus 2y equals to 16 because of the same slope here. So as you, if you need to do the maximize, so as you move it up, it will be more and more, right? Because this one you set the maximum value, the set that you need to find the maximum can get higher and higher value. However, you cannot use the one higher above because the feasible region is right here. So you need to move it down, okay? Do a parallel translation. So as you move it until you hit this line, and you are going to hit really this line because they are parallel, right? So as you parallelly move it, it will coincide with this line, okay? So it means that it's not only this point that will give you the maximum solution, but it also all the point on this line segment, okay, will give you the solution. And usually it will indicate by, you have two points on the same line. You see these 2 points on the same line, that will give you the same value, okay? For example, if you talking about the this point 8 0, you plug in sorry, not 8 0, 0 8, okay, 0 8, you plug in 8 here, you have 32, okay, you have 32. If you're talking about the 8 4, of course, to find the intersection point, you can just simply do a subtraction, right, to get rid of your x, okay? And you have 6y equals to 24, so your y is 4, and as your y is 4, okay, your x can be what? Your x can be 8, so here's the 8 and 4 as your intersection. So you plug in x 8, so you have 16, and another 16, so you have 32 as well. So you got two on the same line that got the same value. So it means that along these segment, it will also give you the same value as well, okay? So you got infinitely many solution along this segment, okay? And of course for your a, which is 0 2, so as you plug in y to be 2, you got 8, which is not the maximum. All right, so let us stop here with several examples in terms of, either bounded region, unbounded region, or sometimes even you got a bounded region but you still have a multiple solution or of the optimal solution, okay? So this multiple or infinitely solution right here, okay, can occur whenever your objective line is parallel to your one of your constraint, okay? So we'll stop right here and continue with several other word problems later. So we'll see you then. Bye bye.